We present our work in this video, learning deblurring texture prior from unpaired data with diffusion model. Since acquiring large amounts of realistic blurry sharp image pairs is difficult and expensive, using unpaired data to train models for recovering sharp images is a more practical and promising solution. Dominant approaches either introduce additional prior estimation and degenerate transformation models, or rely heavily on adversarial learning to bridge the gap from blurry domains to sharp domains, ignoring the complex and unpredictable nature of real-world blur patterns. In contrast, motivated by the fact that blur is spatially diverse and diffusion models exhibit strong generative capabilities, our work attempts to allow diffusion model learn spatially varying texture prior and assisted deblurring in unpaired training restoration tasks. In this work, we propose TP-Diff for unsupervised image deblurring, in which the diffusion model can learn spatially varying texture prior efficiently for blur removal. To our knowledge, this is the first work to integrate diffusion model into unpaired restoration tasks. We propose a texture prior encoder, called TPE, that introduces a memory mechanism to encode texture priors of blurry images in latent space. We propose a texture transfer transformer layer, called teachformer layer, where a filter-modulated multi-head self-attention employs adaptive filtering to remove spatially varying blurs. This is the framework of our method. Our method mainly comprises 4 components: texture prior encoder, diffusion model, deblurring network, and reblurring network. Texture prior encoder is used to obtain the texture prior, which serves as the ground truth for diffusion model training. Diffusion model consists of a diffusion process and a denoising network for adding noise and generating texture prior, respectively. The deblurring network and reblurring network together form the entire cycle structure designed for removing and synthesizing blur, respectively. Within the deblurring network, the proposed texture transfer transformer layer leverages texture prior knowledge to effectively remove blur. Our method adopts a 2-stage training strategy. In stage 1, we utilize the TPE to obtain spatially varying texture prior Z in latent space, and jointly train it and the entire cycle structure for blur removal. At this stage, the Z output from TPE is directly fed into the deblurring network without involving the diffusion and denoising processes. TPE consists of a texture memory enhancement part and a texture memory transfer part. In the enhancement part, we initialize a group of learnable memories and extract tokens from texture-rich sharp images as reference texture templates to enhance the memories. In the transfer part, we search for similar tokens from the enhanced memories and use them to represent texture templates in the input blurry image. We introduce the teachformer layer to efficiently integrate the obtained prior knowledge into the unsupervised deblurring. It consists of 2 components, the filter-modulated multi-head self-attention and the transform-modulated feed-forward network. The filter-modulated multi-head self-attention exploits a proposed adaptive filtering operation to effectively remove spatially varying blurs. In stage 2, we freeze the parameters of TPE and joint train diffusion model and the entire cycle structure. This enables the denoising network to generate a more reliable spatially varying texture prior. Our diffusion model consists of the forward diffusion process and the reverse denoising process. In the forward diffusion process, we first adopt the TPE, in which the parameters are frozen, to generate the texture prior Z as ground truth, and then add noise to Z by the diffusion process and get the ZT with the same distribution as the pure Gaussian noise. In the reverse denoising process, we use the denoise network to generate the reconstructed texture prior hat Z using the extracted feature C from blurry input as the condition and Z as the target. During inference, only given a blurry input image B. We first extract the blur feature C from the blurry input as the condition of denoising network. Then, we randomly sample pure Gaussian noise ZT. After T times denoising process, denoising network generates the texture prior hat Z using ZT and C. Finally, we feed hat Z to the deblurring network, consisting of teachformer, to compute the deblurred result. We compare our method with 15 classical state-of-the-art methods. Our method outperforms other SOTA methods with fewer parameters on GoPro, hide, RealBlur-R, RealBlur-J, RB2V_Street, and RSBlur datasets. We also compare our visual qualities with other methods. Ablation experiments regarding each component demonstrated their superiority in our method. Numerous ablation experiments have demonstrated the advantages of our method. In summary, our method is the first work to integrate a diffusion model into unpaired restoration tasks and propose a novel diffusion model based to fully exploits the beneficial prior knowledge in unpaired blurry and sharp images. Experimental results show its advantages. Thank you for watching.